So our lesson on 9.2 is going to briefly overview how to graph polar equations, but we're going to be heavily dependent on our graphing technology. So I'm going to be using a TI-84 CE, and I suggest you have one handy, otherwise you're just going to be watching me do stuff. I'm not going to make you memorize the names and the types. I think you have a reference sheet of all the different types of polar graphs somewhere in your packet, like on 10 or something on the new packet for this year. But first thing I want to show you is, if I can find it, there we go. This is the link that's in your notes, or at least in our lesson, and it's a bunch of Google images, my face in the way now, of polar graphs. So as I kind of scroll through there, some of them are just the coordinate planes for polars, but you know, some of them are looking pretty interesting. Like this one right here, that's a very cooler polar graph, and my fellow teacher here, she goes, they always remind her of a spirograph, if you guys ever played with that as a child, or a teenager, whatever. But these are the kind of loopy diagrams that we're going to be getting. So remember, polar functions are ordered pairs in the form r comma theta. So we get this weird loop aspect going on. So what I want to do first is I want to explore the first question in your notes, which, thank goodness, someone already filled in basically a table for us. So various theta values off of the unit circle, our famous theta values that we keep using, and the function that they're asking us to graph is up at the top here, 1 plus 2 sine theta in polar form. So, get my pen working, there we go. So here's the function, and again, not going to have to do this by hand. We're going to be using graphing calculators quite a bit today. So if you evaluate theta of 0, you know, we could have done this by hand, but it would have taken us a while, right? So sine of 0 times 2 plus 1. So these are the values that they come out to. So if we start plotting these points, remember how we plot polar points. You start at whatever you open up to the theta, the angle. So 0, and we're plotting at R1. So there's the first point. And then pi over 6 would be this line here. And we're plotting at 2. Oh my gosh. Gonna be tough. Alright, pi over 4 is this line that's not labeled here. This is pi over 4. And that's 2.4. So 2.4, like right here. Or so. Pi over 3 is 2.7. And then at pi over, I'm losing it, pi over 3 pi over 4, excuse me. They're coming back down to 2.4. And then at 5 pi over 6, oh, jeepers creepers, I'm not even plotting the right thing. Back up. I like totally messed up here. Alright, let's cross these off as I go. I did that one, right? Did that one. Pi over 4 is 2.4. 2.4. Alright. Okay, did that one. Pi over 3, here we go. It's 2.7. Check. Alright, skipped over pi over 2 completely. That was fun. That was at a 3. 1, 2, 3. Now it's going to start coming back down. 2 pi over 3 is 2.7. And then 3 pi over 4 is 2.4. 5 pi over 6 is 2. Pi is 1. Where are we at? Pi 1. Alright. Okay. So I stopped checking them off. Here we go. Try again. 7 pi over 6 would be at 0, which is, remember, we call that not the origin anymore, but the pole. And then it starts to get weird. So 5 pi over 4, which would be right here, no, right here, is at negative 0.4. So instead of marking out this way at 0.4, you got to back it up to, like, I don't know, like here, maybe? And then 4 pi over 3, again, it's going to be backed up to negative 0.7. My gosh. Alright, so here's what's happening. We're making like this weird little inner loop. I'm just going to cheat, pretend we graphed all that. So your polar graph for this guy does this. Woo! And you know what? For me, that was a pretty good graph. So here's what I've done, and I want you to do the same. I want you to prepare your calculator to graph a polar. So in mode, I want you to change a few things. Make sure you're in radian mode. And then I want you to be in polar mode instead of any other, normal function mode. And after that, I want you to go to Format, and you don't have to change all this stuff, but I'm going to turn on my polar coordinates, and let's see, it's up to you if you want to try to change anything else as far as like colors and stuff, but turn on the polar coordinates so that way when we hit trace it'll give me the polar points instead of the rectangular points. And then, now don't be confused here, I have two different functions typed in because I was trying to prepare for the next question as well. So this is the function I want you to have typed in, 1 plus 2 sine theta, and then make sure that's plotting, and make sure there's no other like stat plots left on from a previous question. You do not have to have 2 cosine 2 theta in yet, and in fact if you have it in there, make sure you turn it off by de-emphasizing the equal sign. Alright, next thing, window. I went 0 to 2 pi for theta, and then I don't know what it's counting by right now, it was something. I think I squared it off later. And then after that, I mean, you can set up x min and y and max and x x min x max y min y max to be -5 and 5 if you'd like, but I just went ahead and hit zoom square and kind of played around with it that way and figured out what happened, and that's what it was supposed to look like. So this has a funny name. It's called a Lima Sun. So we call this sometimes the lima bean one. So it's not called a lima bean, by the way. It's called a Lima Sun, and this is how it's spelled. I do not know what that letter is. I never took any sort of French or Spanish, whatever language that letter is from, but Italian, I don't know anything. I know German, and that wasn't in the German alphabet. So this is Lima Sun. That's the name. And on your reference sheet on page 10, I think, of your notes, they give you various types that we're going to see. And today we're going to focus on the Lima Suns, and circles are going to show up today. And then, the rose, which surprisingly enough looks like a flower. Alright, so this next one, I am not going to bother doing anything by hand anymore. I'm going to go to my calculator. In y equals, I'm going to go ahead and delete the previous one, and I would like y'all to get 2 cosine 2 theta typed in. Again, make sure that your mode was polar, which if it says R, it is in polar, and make sure that your radian mode is on instead of degree, and also you might want to turn on your polar coordinates. So, pause the video if you're not set up, but I'm ready to rock and roll. I'm going to hit zoom square again, just in case something's weird. Oh, that's nice. This is called a rose. Looks like a flower to me, but they call it a rose. So these can get pretty complicated, but this function is in the style of a rose. I can tell that because anytime you have a function that is some sort of a number, and then it's cosine or sine of, and then there's some other number, theta. If it's in this format, we're going to have a rose. Now, these numbers tell me something. For instance, this number right here tells me the length of the petal. And yes, they call them petals, like a flower petal. And then this number here is a little complicated. If this number is odd, okay, pen, you want to work, come on. If this number is odd, that means it's the number of petals. So like if it was a 3 theta, you'd have 3 petals. But if this number is even, then it's 2 times this number is the number of petals. So like for instance in this question, that number was a 2. So you noticed on our rose we had 4 petals, because 2 is even, so then they double it, and that's how many petals I should expect. The other thing I want you to notice and point out to yourself when you go to graph it is that the petals themselves go 1, 2. You see they go 2 up, and that was the number in front of the polar function, or the polar equation, was a 2, so that tells me the length of the petals. So I don't expect you to be plotting points here, guys. I just want a real rough estimate. It goes out to R2, and you end up with something like this. There's always some beautiful symmetry on these roses, so that's nice. It'd be even nicer if I knew how to graph. So bad. Okay. Alright, so here's all the stuff we just covered. That's called a rose. The length of the petals were 2, and it has 4 petals. That's because of all that information we just spouted out to you. So here, because it has that same format, if you want, or if we were just matching stuff up, I know that we're going to have another rose. And what I know about this rose is the petals are length 2, or I should say R equals 2, huh? That makes more sense. And then inside, there's a 1. So since 1 is odd, that means we would have 1 petal. Now this is a little confusing, because if you think about one of these things having 1 petal, and then having a length of the petal of 2, well, it's going to end up basically looking like a circle. So if you don't trust me, that's all right. Let's go graph it. So we have 2 sine theta. Delete that 2. See? So a very boring rose that just has 1 little petal, and there has to be some beautiful symmetry to it, so you're making a circle, basically. So that's interesting, right? Kind of weird, though. The circle starts, like it bottoms out here at the pole. And then, yeah, I'm supposed to be drawing this symmetrically, but you know that's not going to happen, so use your imagination. Hey, that was pretty good. All right, I'm going to call that a win. All right, so here, this is going to be, if you could make a prediction, that'd be cool, but it looks a lot like that first warm-up problem we did, where I eventually told you it was a Lima Sun. We're going to have a cute little Lima Sun. I want to go to graph this. Let's go ahead and graph it. Basically, it's the same thing as we had, but isn't there just a +2? So, at the end here, I'm just going to put a +2. My calculators are just slow. And we get this. So, I don't know what you would like to call this. If you're a sweet little angel like I think you all are, you're going to call this a heart. But if you're like many teenagers out there, they usually the first thing they say is that this looks like a butt. Yep, my 8-year-old agrees with you. So keep that in mind, that you have the maturity of an 8-year-old if you thought that looked like a butt. Alright, so we have what's called a dimpled Lima Sun, and also known as a cardioid. The word heart, cardiovascular. So they think this looks like a heart in the math world, so they started calling these cardioids, but I think your book refers to this as a dimpled Lima Sun. Again, I don't expect you to be graphing this really, really accurately. I do expect you to kind of notice how far, like, up and down, right and left on the polar and the, oh boy, theta axes they go. But it does have this little dimple at the pole. And then, let's see, it goes 1, 2, 3, hello, 1, 2, 3, 4, up to R4 for that top part. So I'm going to let you have fun graphing that one, since apparently I am not so good at it. So 1 minus 3 cosine theta. Maybe you have a prediction for what this looks like. I don't know. Let's find out. If my calculator comes back, that is. Oh, man. Okay, so my calculator is not behaving right now. So I'm just going to tell you what it looks like. But I would like you to pause the video and actually graph it so you can get a better picture, because what I'm about to draw is going to be really awful. We're going to have another funky little Lima Sun. It's called a Lima Sun with an inner loop. So, it's a little difficult for me to tell how far my picture goes out because I can't draw. But the inner loop, I think, goes out to 2. So, basically it's looking something like this. Now, the outer loop was supposed to go to 1, 2, 3, 4. Let's see. 1, 2, 3. Hey, you know what? Pretty good. I was supposed to go out that far. I kind of freehanded that, obviously. It's a really rough drawing of what it's supposed to look like, but this is a... I never spell this right. I don't know what that letter is, that thing with the little squiggle on it on the C. So the Lima Sun with an inner loop. You do not have to know the name of that, but just don't be surprised when you use your graphing calculator and you get something that looks like that. Oh, sure, now it works. All right. So I didn't graph that one on my calculator. Please do it yourself if you want. We do need to talk about symmetry. So if you have a graph that has what we used to call y-axis symmetry, remember there's no x or y-axis anymore. So this axis right here is known as theta equals pi over 2. That's the angle for theta there. So if it looks like that, then you say it has symmetry with theta equals pi over 2. I know that's kind of a mouthful, but that's what you got to say. If it has what we used to call x-axis symmetry, you're going to see that we don't call it x-axis anymore. We call this the polar axis. And then if it has symmetry of what we used to call origin, but now we call the pole, it has symmetry with respect to pole, the pole. So if I go back and I look at, well, I didn't draw mine, did I? Alright, I better go back and draw mine real quick. Number 2. This was the heart-shaped one, if you want to call it that. So, yep, totally nailed it. Alright. If you actually graphed it symmetrically, you would probably see that the symmetry line is right here. So this one has symmetry of theta equals pi over 2. And then this was that, the one with the inner loop. I thought I graphed that one. Oh, I did. I just graphed it on the wrong screen. Alright, so it looks like this, or so. Like this. I didn't graph it so hot. What's new? So it has symmetry of polar axis. I think I skipped one earlier. We had that circle up at the beginning here. So the circle, we can't even draw a line today. The symmetry of theta equals pi over 2. It's not how you spell symmetry. Symmetry of theta equals pi over 2. And, I don't know, oh, I drew that one. That was kind of nice. This one's kind of confusing. It has a lot of symmetry. It has the theta equals pi over 2 symmetry. It has polar axis symmetry. It has symmetry of the pole as well. So basically, that rose is super symmetrical in various ways. Let's make a note here on our symmetry that if it has this type of symmetries with pi over 2, that means that its parent function, its parent trig function within you, is the sine function. And if it has the x-axis symmetry, what we used to call it, which is now the polar axis symmetry, we're looking at cosine. So that's like a dead giveaway when you're trying to graph a polar equation with sine or cosine, and the question is about symmetry. You could probably make a guess based on the function, but of course we're going to be graphing ours on the calculator. I do not need you to know how to test for symmetry, so we're going to skip over that part completely. So this is what's in your textbook, some really nice pictures of what they're supposed to look like. This is also on some worksheet in your packet. I think it's 10. So they can get kind of fun. So our next, oh, we didn't even talk about this one. This one's kind of cool, the spiral of Archimedes. I love how they phonetically spell it for you in case you didn't know who Archimedes was. Those are cool, right? Look like shells to me. I like them. Not doing this business, skip it. Not doing that business, skip it. We already did the symmetry. Alright, and then it says try without the calculator. And then this is how far I scratched it off for her kids last year. But you know what? Let's think. This is a lot like our rows that we were graphing. So we are going to have a rows. And this number in front tells me the length of the petal. So the length is 4. And then the number inside the sine function is odd. So that means we have 3 petals. So what you do is you type this in your calculator, and for the sake of time I'm going to kind of skip that part. But the first petal is, I think it's down here. Yeah. And remember it's length 4, so, oh boy, 1, 2, 3, 4. It's supposed to go all the way down to here. And then these petals are symmetrically placed about the pole. So if you think about, you know, a 360 having 3 petals, I know it's not 360, it's radians, but whatever. So 60 degrees. So if I travel 60 degrees, you know, away from where I just graphed that first petal, that's going to bring me to, let's see, right here, pi over 6. The petal's too long. Alright, try again. Totally. And then up here at 5 pi over 6. Oh man, gosh. So this, to me, looks a lot like a wind turbine and its blades. Just want to throw that out there. I don't know enough about wind turbines to know if there's a direct application. But what is cool about, I forgot to mention this on the other lesson, the polar graphing, it's used by like people who need to control air traffic, but also things that are in space and the atmosphere, because if you overlay like a polar axis on like a top view of the planet, that's kind of how they measure things out, as on a polar axis. So, food for thought, in case you're curious. 3 cosine 2 theta. Again, we're going to have another rows. This time, the length of the petal is 3. And then be careful, because remember, when the number inside is even, that means we have to double that number, and we're going to have 4 petals. So I'll take the mystery out of this, guys. The petals are on the quadrants. So 1, 2, 3. First petal. Boom. Second petal. Oh man, I missed. What? Oh, man. I'm getting worse and worse. Oh, boy. That was good, I think. Totally. All right, nailed it. This, by the way, has lots of symmetry. We talked about that on the last symmetrical rows like this. This one here, this has like rotational symmetry. I don't want to talk about symmetry on that one. We're gonna back up. At the end of your worksheet here, there's some follow-up questions that are just kind of synthesizing all the information we just covered. Let's put it all together. So I want to know if you could figure out whether we have a Lima Sun, a rose, or a circle. So a circle and a rose look the same at the beginning, but a rose is only going to have one petal, which this guy does not have one petal. And this is a rose. The Lima Suns are in the form like some sort of a number plus a sine or cosine function. So until you have that format, you're not going to have a Lima Sun or anything that looks like a Lima Sun. I never pronounced this one right. Let me look up the phonetic. Lemniscate, I think is how this one's said. Basically, it looks like an infinity symbol. It's kind of cool. It looks like this. So if you ever see that, that's what that's called. We haven't even talked about it, so you can imagine I'm not going to ask you about that on the test. And then this question here is a nice reminder of how we can use the polar axis on an application. So here's our ship. And right now, they want to know where it's located with polar coordinates. So they want to make sure that your angle is between 0 and 180. So keep that in mind. So I'm only allowed to use basically these thetas here. So I need to back up on this axis and call it 150. Oops, that's in the wrong spot, Abruzzo. 150. And then I'm going to have to back up 1, 2, 3. So -3 for our R. Very good. A little reminder from yesterday. They want me to graph R equals 3. Again, a reminder from yesterday. So you go to the third loop, 1, 2, 3. And you trace the R. That was pretty good. I'm going to call that a win. And this question, find the distance between the points with these polar coordinates. So remember you had that weird funky formula, and we just decided to graph these when we were doing these questions. So 150, 1, 2, 3. And then 45, which is right here, but then backing up -2. So right there. So this point here is, so this is the ordered pair -245, but I think it would make more sense for us to call this without the -r. Let's see, that would be 225. 2. So 2, 225. There we go. And they want to know the distance between them. So basically we're doing one of these questions, which ends up being a log cosines question. Clearly this is a 2, and this is a 3. And your job is to figure out the angle between these two. Well, that's pretty easy to do now that I have 150 and 225. I'm just going to subtract those. Was that 75? Yeah, 75 degrees. It's right there. So when I set up my essentially law of cosines question, this time make sure your calc is in degree mode. I know we've been in radian this whole time, but if you're typing this, you need to be in degree mode. So 2 squared plus 3 squared minus 2 times 3 times the cosine of 75. Square root it at the end if you haven't already done so, and it comes out to approximately 3.1. And they don't give me a label, so I'm just going to call it 3.1. Alright, and then this is one of the new things here. It's in that format, number and then a trig function. So we're going to have one of those Lima Bean, Lima Sun things. And yeah, I'm not going to graph this so hot. But basically it's one of the dimpled Lima Suns, which is cardioid in shape, or for those of you immature students, the butt. Alright, good luck.